So in this video, we're going to discuss the uniform distribution for continuous data and a normal distribution for continuous data. Most of these topics this week are just in theory and talking about different shapes and what it means to have different shapes like bell-shaped curves. But the really intense probability calculations for continuous data is going to be calculated when we start talking about the standard normal curve. So for continuous uniform distributions, we learned about in a previous section discrete uniform distributions, which recall the difference between discrete and continuous have to do with how they're counted. So a discrete distribution or discrete variables rather, are those that can be counted. So like people in attendance in class. I can count the students who have attended my class, 1, 2, 3, 4. There's no half a person or quarter of a person between person one and person two. Cars on a highway, I can count the cars. But continuous data has those decimals, those infinitely many numbers between 0 and 1, between 1 and 2. So like time and distance and measurements of weight and those types of things. So even though the idea of the shape of the distributions are the same from continuous to discrete, the variables or the numbers that we're working with are completely different. So when we're working with these probabilities, we have to now, it's not going to be as cut and dry as the discrete data, because discrete data, it was the probability of exactly 2 or the probability of exactly 3, and nothing existed between 2 and 3 to find probabilities of. But in the continuous world, we will be needing to consider all of the infinitely many decimals between 2 and 3 when considering probabilities. And therefore, the way that we conduct probabilities for continuous data is going to be significantly different than discrete data because there's infinitely many probabilities to check, and we can't possibly run a formula for every infinitely many possibilities between two whole numbers. But that's for a future date. Let's discuss what these distributions look like and a little bit about how to handle them. And that's what we're focused on this week. So there are two types of uniform distributions, the discrete and the continuous, as I was talking about. Conceptually, both uniform distributions distribute probabilities evenly across the sample space. For the continuous uniform distribution, the probability density is spread out amongst the range from some point A where you start to some point B where you complete or finish. So if you look here, we are looking at a real number line, but in order to define the uniform distribution, you have to have a starting point A and a finishing point B. And the height of this rectangle is calculated by 1 over B minus A. So the uniform probability density function is given by the following, and the way that we would read this is that the y value, f of x, is just function notation for the y value. The output, the y value, is equal to 1 over b minus a for any x values, any inputs that exist between the interval, the starting point A and the finishing point B. If we're looking at x's outside of this interval, so before the rectangle begins or after the rectangle ends, then our height will be 0 for a uniform distribution. It doesn't make sense to consider values outside of the interval a to b when we are working with the uniform probability density function, and therefore that's why they're set to 0, because they will not give us any meaningful data. The mean and the standard deviation are given by the following expressions. So the mean, which we've also learned, is the expected value. So they're synonyms. So if you have a question asking you to find the expected value, that's just the same thing as finding the mean. And you would do that by a very straightforward calculation, which is the average calculation of adding and dividing. So you're taking an average. And the standard deviation, this square root of 12 is standard in this formula, and you do b minus a in the numerator. Let's take a look at an example. So the fire department records how long it takes each of its trucks to reach the scene of a fire. Suppose the distribution of arrival times is uniform with the minimum time being 2 minutes and the max being 15 minutes. Let X equal the time it takes the truck to arrive at the scene of a fire after being called. So, what is the probability that a truck will reach a fire scene within 5 to 10 minutes? Is one question we want to answer. Second question we'd like to answer is what is the expected time until arrival of the fire truck? And third, we want to answer what is the standard deviation of the arrival truck times. So for part A, calculating the probability is simply calculating the area of the rectangle. So one thing that we're going to learn is that the area under these curves is the probabilities, which is why we'll see that all the areas under the curves add to 1, just as we learned our probability distributions, all our probabilities add to 1. So if we wanted to calculate the probability, and again, the question was for the uniform distribution, the probability, here you go. What is the probability that a truck will reach the fire scene within 5 to 10 minutes? So we're going to take the area. So we have 1 over b minus a, so 1 over 15 minus 2, because they stated that the minimum response time is 2 minutes and the maximum response time was 15 minutes. That gives us a height of the rectangle of 1/13. The width of the rectangle has to do with what the question's asking for us. The question's asking about the probability between 5 and 10 minutes, and therefore we would subtract 10 minus 5 to get 5 for the width. So if we calculate the area, which is length times width or height times width, same thing, we multiply 1/13 times 5 and we get a probability of 5 over 13. Indicating there's a 5 out of 13 chance that the response time for the fire trucks will be between 5 and 10 minutes. So here's the picture of the rectangle from 2 to 15. It's assumed to be uniform as stated in the problem. The height was calculated by 1 over b minus a. The 5 to 10 is shaded in blue. That's the area or the probability that this would occur, that the response time would be between 5 and 10 minutes. And that's why the probability calculation was simply length times width, because with uniform distributions, all of probabilities are going to be rectangles. The expected value of a continuous uniform random variable is given by the mu formula, which is a simple average formula, adding a plus b and dividing by 2. So 15 plus 2 divided by 2 comes out to 8.5 minutes. Therefore, the expected time until arrival of the fire truck is 8.5 minutes. The standard deviation is given by the formula b minus a over square root of 12, where square root of 12 is standard. That's not going to change from problem to problem. So we do 15 minus 2 over the square root of 12, and it comes out to approximately 3.753 minutes. Okay, now let's talk about the normal distribution, and the normal distribution that's not uniform. So that means the heights can vary from one point in the graph to the next. The normal distribution, originally called the Gaussian distribution, was named after Carl Gauss, published a work in 1833 describing the mathematical definition of a distribution. Gauss has done a lot of work in the mathematics world, and he has many theorems and many contributions to mathematics as a whole. So this normal distribution curve is just one of many of his works. Normal distributions are bell-shaped, but the bells come in various shapes and sizes. Since all normal distributions are symmetric, and symmetric meaning just like in kindergarten when you had to create a heart for Valentine's Day, your teacher instructed you to fold the paper in half and draw half of the heart so that when you cut it out, it may not have been a pretty looking heart, but at least it was symmetric and it was mirrored on both sides of the heart. Okay, so since all normal distributions are symmetric, the mean, median, and mode would all be equal. Recall, we use the mean and median often to determine the shapes of distributions. When they're equal, we are indicating a symmetrical curve. If the mean is greater than the median, it's skewed right. And if the mean is less than the median, it's skewed left. The total area under this curve equals 1. Again, for the same reason that probability distributions, one of the two characteristics we need to check for is that all the probabilities add to 1. So because we are considering all probabilities in a data set, the area is the probabilities, and therefore the whole area under any one of these distributions, statistical curves, will be equal to 1. And this is just stating that what we have just spoke about, which is that the probability is the area. Although a normal distribution has a bell shape does not imply a normal distribution. So be careful if you see a bell shape, you cannot assume that it's normally distributed. It just has a bell-like look to it. In the figure below, which we can't see yet, there we go. In the figure below, the shaded area represents the probability of being within one standard deviation around the mean. Recall from the empirical rule that one standard deviation left and right of the mean encapsulates 68% of the data values, specifically 0.6826. And similarly, as we learned with the empirical rule, two standard deviations out encapsulates 95% of the area under the curve, and three standard deviations, 99.7% of the curve. The normal probability density function is given by a really hideous formula. Luckily, we don't need to use this formula to calculate probabilities or heights of the function at any given point in the curve. If you're wondering where this function came from, that would involve calculus. So asymptotes would describe what's going on with the function and its end behavior. And the function itself is derived through calculus. So if you take a calculus-based statistics, you would be able to derive this function and how we got this formula for the height at any point in the curve. But again, we will not need to use this calculation because we will do most of our calculations using something called the standard normal curve, and that comes with pretty formulas that we'll learn how to do in our guru. So a couple things to note is the normal distribution is a theoretical construct of a bell shape. Therefore, it would not be unreasonable to expect data drawn from a normal population to exhibit the bell shape characteristic. In two small samples taken from a normal population on the next slides, the data does show a faint resemblance of a bell shape, but as you can see, the shapes of the histograms developed from these small samples are somewhat unpredictable, even to some extent apparent. So here is a small sample size of 25, and we can see that there is vaguely a bell shape. This one looks more binomial than anything because, not binomial, bimodal, because it has two humps here. This isn't too pretty, but again, we know that it's coming from a normal population, so we would consider it bell shaped, but we are going to discuss about how probabilities are calculated, and there is going to be a discussion about what is the minimum sample size that we can use that will be sufficient for calculations, and what would we have to do if we have a very tiny sample size, such as 25. And that's going to be further discussions in future sections. Here's another example of a small sample size. This one looks a bit more bell-shaped, not perfectly symmetric, but it definitely has more of a bell-shaped resemblance. For large samples, the representation of the bell-shaped curve is usually more visible. While the large sample of 200 certainly is not a perfect bell-shaped curve, it is recognizable. So now we're seeing a tall bar in the middle and it tailoring down on either side. This isn't perfect. There seems to be a bit of a elongated tail here. But the larger the sample size, the more accurate the curve becomes, and therefore the more accurate your probabilities become as well. So that is just a small discussion about normal distributions and uniform distributions for continuous data.